So we're going to do the next couple of sections in the notes. So we're going to start looking at further differentiation and indices. Okay, so we're really applying our index laws that we've learnt way back in chapter 2, chapter 1 even, okay, and applying those to these examples. Okay, example A, f of x is the square root of x. Squeaky old thing. Okay, so we want to use the rules that we have used in the past, okay, and use the shorter method of differentiation to be able to write down the derivative of the square root of x. So, first things first, we need to rewrite the square root of x using our index laws. Does anyone remember? Okay, so x to the power of a half means the square root of x. Okay, so once you've got that, we can then apply our differentiation rules. F dash of x. Alright, so we bring the power down to be half of x, and then you need to decrease the power by 1. With half, take away 1. And then at this point, you need to rewrite it back into the question format. So instead of having fractional indices, we're writing them as thirds. So, who remembers what happened? Let's do m to the minus n. Who remembers that rule?
Is it n goes in front of the square root? Like,
Nope, only when fractions are involved. Nope. Who remembers the index laws? Negative index, we do what?
It doesn't have to become a fraction.
Sorry?
It doesn't have to become a fraction.
It will become a fraction, yes. Do you remember what that fraction is? 1 over m to the power of n. Okay, so everything but the minus sign goes on the bottom, and 1 goes on top. Okay, so that's what we need to do here. There'll be 1 over 2x to the power of half. Applying your index clause there. 2 is already at the bottom of the fraction, and 1 is already up the top. Okay, so 1 over, and then going backwards from here to here, you need to rewrite it back into the format of the question. Alright, so that is the derivative function. Okay, so who remembers what the derivative function allows us to do?
The gradient of the tangent of the
The equation of the gradient of the tangent. Okay, alright, you need to remember that equation, gradient, tangent. Alright, so if I had to draw the graph of square root of x, and we'll cover that in our functions and graphs. Okay, if I take the point where x equals 4, what's the gradient of the tangent? Hey? X equals 4?
into this.
Uh-huh.
1/4.
Yes. Right, so what's the square root of 4? 2. 2 times 2? 4. So the derivative of the tangent at that point is always, is going to be 1/4 at x equals 4. Does anyone notice anything about whatever value I substitute into the derivative function? Well, what values of x am I restricted to? Why?
Because with f of x, the first if it's a negative, it's not a real number.
Yeah, so you take a square root of a negative number, it won't come back as a defined number at all. Okay, so we can only take the square root of a positive number. okay, and it will return a positive number, okay, in this application. That means the gradient will always be, okay, the gradient will always be, at any point x on the curve, it will always be positive. Alright, B, f of x is 1 over x. Okay, so this is further differentiation, so really what we need to do is set it up so that we can differentiate. Okay, I'm telling you now that I really don't want to have to go through this using first principles, okay, because that'll be just a nightmare with fractions involved as well. Alright, so you need to know your index laws to be able to manipulate that so that you can use your shorter methods of differentiation. So, how can I write 1 over x using some index laws? Just about. Equals x to the power of negative 1. Okay, so what that allows be x to the power of 1 on the bottom of the fraction, which is just x, and you have the 1 up top. Okay, so now you set it up using your index laws, we can now differentiate nice and quickly. So you bring the power down out to the front, multiply by any coefficient that is there, and you need to decrease the power by 1. Were you telling me the answer, or were you telling me this? Were you telling me this step, or were you telling me this step?
I was telling you the first step.
Okay, so let's fix it back up so we get something looking like the original function.
What?
I didn't hit my paper.
Lucky they didn't hit me, eh? Right, so how do I rewrite that back into the format of the question?
Well, negative 1 over x. No, 1 over x squared.
Good. Negative 1 all over x to the power of 2, x squared. Okay, C. Any questions so far? Alright, 3 outside the cube root of x. Okay, step it up here. 3 outside the cube root of x.
Not even close.
Alright.
Is that 1/3?
Good. When you have a fractional index, that is a fraction, the numerator goes with the power inside the third, and the denominator becomes the third power. Okay, so when you had x to the half, the numerator goes with x, whatever's inside the third, and the denominator becomes the third power. Okay, now by default it is squared, the square root, so we don't need to show that 2, and we don't need to show that 1. However, now that we've got the cube root, okay, means we need to have the index of a third. Okay, and of course if that was at the bottom, you have to put the negative sign there as well. Alright, let's differentiate. So, you bring down that power, multiply by any coefficient, there is out the front, so it'll be 3 times a third, lots of x to the power of a third, take away 1. Negative 2/3. Alright, so what is 3 times a third? 1, okay. let's see if we can all rewrite x to the power of negative 2 over 3 into third form. So the first step, when you had the negative index, 1 over x to the power of 2 over 3. And now I want to write x to the power of 2 over 3 into third form. So what? Good. 1 over the numerator of the fraction index goes with the base, so it'll be x squared, and the denominator becomes the root power. Okay, and that was covered in your index laws earlier this year. Right, so it's good. We're revising our index laws. Okay, and you need to know them. Prove what?
Square root of something.
How do you know? How do they find it?
Yeah, I wondered that question myself. But yes, I will have an answer for you when I get it. Alright, D, find the equation of the tangent to the curve y equals x to the negative 1. X to the power of negative 1, sorry. At the point where x equals 3. So we're combining yesterday's work, tangent to normal, to today's work, to the previous last week's work. 3 lessons worth of stuff we're doing now. Okay? So, we need to find the equation of the gradient of the tangent by differentiating. Find the gradient of the tangent at x equals 3. And then from that, I want the equation of the tangent at x equals 3. Okay, so when I have a y at the front, the notation for the derivative is y dash equals negative x to negative 2. Okay, bring down the power, take 1 off the power. Right, so negative 1 over x squared to help us a bit further, but we do not need to write it like that because I'm not needing it back in this form because you are actually applying the question. Okay. So we need to find the equation of the gradient of the tangent at any point x for that curve. Okay, which is a hyperbola, which we'll cover next topic. Right, so now we need the gradient now of the tangent at x equals 3. So every time there's an x, we substitute in 3. And this gives us the m, the gradient that we need for our point gradient formula.
Oh yeah.
Okay, so we need the equation of the tangent straight line. So to find the gradient, to find the equation, we need the gradient and we need a point. Okay, do we have both those things? Alright, substitute my m's. This will be my x1. But I need my y1 still.
It's just Y.
Okay. It's just what?
Is it just Y?
No. Well, I need the actual coordinate. I don't have the y point, the y value of the coordinate, don't I? So how do I find it? How do I determine it? you have an equation relating x and y. Okay, so when x equals a third, so y is 3 to the power of -1. And using index laws becomes a third. So 3 comma a third is a point on the curve y equals x to -1, which is a hyperbola. So now I have both bases of the coordinate and I have the gradient. I can now substitute into here. Right, tidy up y equals mx plus b form. That's a 9, that's a 7. So, y equals -x over 9 plus 2/3. The line in the form y equals mx plus b tells us what two things? What two things can I get out of this equation?
Gradient and one stuff.
Good, okay, so the gradient is the coefficient of x, which is -1 over 9, which is what we're expecting when we rearrange it, okay, and the y-intercept, where it cuts the y-axis. So if you were to graph it, you could use those two bits of information fairly quickly to be able to put it onto a number plane. Alright, so that's 8.7. Alright, I'm going to do the next bit.
Function of a function.
Yep. Right. Function of function. Are there any questions about anything we've done so far today?
Oh, this is the one that's to have
Page 66 in your notes. Yeah, that was 65 from before. And we're up to page 66. Okay, so a function of a function, which is also called a composite function, is a function made up of two or more other functions. Okay, So for example, 2x take away 1 to the power of 4, okay, is an example of a function. Okay, so it's usually got some power, got some linear or quadratic or further in a bracket to a power out the end, sorry. Okay, where we can make it up into two separate parts. Okay, so we can make a substitution, let u equal 2x take away 1, and we'll apply the result that we're about to look at through the examples. So, to differentiate a composite function, we use the following rule. So, dy over dx is going to be dy over du times du over dx. Okay, this is what's referred to as the chain rule. So what we need to do is make a substitution and then do some differentiation. To make it more clearer, what we're doing with some examples. Alright. So examples. Let's differentiate the following. 2x plus 6 all to the power of 3. So it's not so straightforward, not so obvious on how we're going to differentiate this. Okay? Because it's not just bring the power down and decrease the power by 1. Okay, some extra steps that we need to do. One alternate method we could do is we can expand the whole thing out. Okay, we could do that, but it will take a bit of time. Okay, so we're going to look at this chain rule application. So, let u equals 2x plus 6. So whatever is inside the bracket, I'll set it to variable u. Let's put out the front of the question, y equals. Okay, now if I let u equal 2x plus 6, what can I write down for what y equals using what I've just used?
U to the power of 3.
Good. U to the power of 3. Okay, so made the substitution. So I've got a u equals something in terms of x, and I have a y equals in terms of u. Alright, so here's your rule. dy over dx is dy over du times du over dx. Alright, if you notice the diagonal, alright, so I've got du and du, so the same thing, so I can cancel them, right, and all I have left is the dy over dx, okay, which is what I've got at the front. Okay. So, I need to differentiate y with respect to u. That's the notation. Okay, so whatever's at the top is the start of your equation, and what's on the bottom you are differentiating with respect to that variable. Okay, so dy over du, what's the derivative there? What's the derivative of u to the power of q? U to the power of 3. 3u squared. Okay, so you can look at it as x's and use the same rules. So we've got the variable as u. Okay, so I'll now have my dy over du, which is equal to 3u squared. Now I need my du over dx. So I've got my u equals something in terms of x. So du over dx equals what? What's the derivative of that? 2.
Wow, it's a lot easier than I thought. It looks nasty.
Always would be when I introduce things for the first time. So dy dx, this is the derivative. Okay, so it's like so I've told you y dash dy over dx and f dash of x is your 3 common notation for the derivative. Okay. Right. So dy du so equals 3u squared times du dx, which is just a constant t. Equals 6u squared. And I have made a substitution for u, so I'm going to go back and put the value of x back into it. Equals 6 outside of 2x plus 6, or to the power of 2 squared. Yeah. And that's how we can differentiate, and that is the derivative function for that. So, I've got one more example, and I'm hopeful when you're looking at this one again, and when we're working through the second one, okay, you're going to notice something.
No,
Alright.
Leave that one like that.
Say it again.
So you just leave it as...
Yep, for the time being. Alright, so I'm wanting you guys to notice something. And Amanda, if you work it out, let me know.
It's on the sheet though.
Hey?
It's on the sheet.
Oh, really?
Anyone knows a faster way to do this? Do now.
Right, that's my poor setting out from the start. Alright, B. We now have y equals x squared plus 3x plus 2, or to the power of 8. So, Maguila, you will be learning a quicker way to expand that in your HSC course for Extension 1. Okay, instead of trying to do it bit by bit. Okay, but we'll worry about that when we get up to it. Okay, so let u equal everything in the bracket. Okay, which means y equals good. Y equals u to the power of 8. Alright, so our chain rule, dy over dx is dy over dx, like that. And then we need to put the new variable in. Okay, so that's the other way to look at it. So we du over dx. So when I was at uni and I was doing my mathematics course and my engineering course, they would keep referring to the chain rule a lot, and they keep referring to this a lot, and I didn't remember doing it all in high school. Okay? That's why I'm showing you now. So when you get told about the chain rule, you've got a pretty good idea now what's going on. Alright. So dy over du equals what? Good. 8u to the power of 7, differentiating that. Differentiate y with respect to u. And du over dx. Good. Does everyone see where that came from? Yep. Differentiate u with respect to x. Alright, so your dy over dx is dy du, 8u to the power of 7, times du dx. Alright, so 8 outside of 2x plus 3 times u to the power of 7. I'm not going to expand it. I'm just going to leave it as it is. And I'll then substitute the value in for u into the answer in the bottom. Okay. That's the derivative.
I really, I like how we just leave it like that. Really, I do.
For the time being, yeah. Because you're not asked to expand, you're not asked to factorise, you're asked to write down the derivative, write down the derivative for me. Question?
Derive and expand.
No.
Did you have a question, Amanda?
No, just thinking about.
Yeah? Oh, just before I saw your facial expression suggests that you might want to ask something. No? Oh, I should have mucked it off. Okay, so did anyone notice the quicker way to do it?
Yeah, I don't think I don't know what the quicker way is, but the only thing I've noticed is that the power ends up out the front, and then it's
Yeah.
times by the
Good.
bracket, and then the power is always one way.
Alright, so we're getting somewhere? Anyone else add to that?
I can see it, but I don't know. I'm reading it right here. Don't know how to tell you it to look smart, but it's here.
Oh, wait, I think okay, I see it. You can go.
Well, the first half is the what's called a derivative
Yeah.
of the
The
first
short
bit. Yeah, that bit.
Yep.
And the second half is that with one less power.
Yeah.
Yes, and where did this come from?
The
It's
derivative
power.
of the and then the
Excellent, so you two combined it to get the answer.
Oh, man, I saw it. Oh.
Very good, both of you girls. Alright, so that's the quick way to do it. So, the result dx of some function of x all to the power of n.
So I didn't know what it was.
Okay, this is in your notes. So some function of x all to the power of n, so like this one, all to the power of 8. Okay? Bring the power out the front, multiply it by the function of x, and we multiply by the derivative of the function inside the bracket. Okay, that is the quick way to do it. So, and take away 1.
Yeah. Oh no, it's just the opposite
Yep.
way around. That's all.
So when you bring the power down, you've got to decrease it by 1, but further on you need to then multiply by the derivative inside the bracket. Okay, so let's have a go with the same two examples.
Yeah, it is.
So y is 2x plus 6, all to the power of 3. So these are the same two examples. Let's now incorporate that. So you bring the derivative down,
This is another one of the last one.
2x plus 6, decrease the power by 1, and then multiply by the derivative inside the bracket. Okay, so when we set du dx, we got to 2 for that example. That's where that came from. So tidy it up. So be 3 times 2, 6 outside of 2x plus 6, all to the power of 2.
Wow, you've done it again.
Okay, so I've shown you with the chain rule, and I've now shown you with a quicker
Twice.
method, I guess. We call
Twice
it-
in 1 week you've done that. Here's something really, really long. And then
That
here's
was really,
something-
really long, was it?
No, not really long, but long enough. And then here, do it.
No, it's fun because you get to pick up on patterns and it's like, oh, I know what's happening.
Good. That's why I teach it. So you identify pattern. Y equals x squared plus 3x plus 2, all to the power of 8. So that is one very complex function. It's got lots of places where it's turning and doing all sorts of doing all sorts of what my maths teacher would say, all sorts of weird and wonderful things. Right, let's differentiate. Bring the power down. Everything inside the bracket, rewrite. Decrease the power by 1. Then multiply by the derivative of inside the bracket.
Yeah.
It's the same answer.
Same answer, but the other way.
And I was expecting that, wasn't I? Alright, it doesn't really matter the order you write it. It's 8. I'm just going to write it like that. 2x plus 3. X squared plus 3x plus 2.
Around.
Okay, 7. I'll just rewrite it like this. That's what done. You don't have to. You can write 8 outside of that and put the bracket next to it. That's
I just skipped it completely.
Yeah, because on the sheet, it's swapped
I just
around.
went straight from the first to the last.
Not meant
as
to.
long as I'm getting the right answer at the end.
Yeah, on the.
Okay.
However many or little steps you need.
As long as it's the right one.
Okay, so we of course had the application to this style question for finding tangents and normal. Oh, there's no more. Right, let's do it quickly.
Yeah.
Now I want to find the equation.
Oh.
Let's do the first one. Be a bit quicker. I want to find the equation of the tangent to the point, this one, at the point where x equals 2. I want you to now find the gradient, find the equation of the tangent at x equals 2 for this curve here. Well, I'll waste a good 4 minutes where we can do some normal application. Alright, so from A, I want to find the equation of tangent at x equals 2. And I'm pretty sure there's a question like this in the exercises anyway. Right, so we've already worked out y dash is 6 outside of 2x plus 6 all to the power of 2. So at x equals 2.
Oh, yeah, so it is.
Okay.
No, we have to get the equation. 600.
Pretty
Yeah.
sharp there, isn't it?
Yeah.
Y dash is 6 outside of 2 lots of 2 plus 6. So 6 lots of 4 plus 6, 6 lots of 10, all to the power of 2. Yes. So we've got a gradient of 600. Hey, it works. Alright, so I've got the gradient. I've got my x value, which is 2. And I'll need the y value for the tangent to substitute into the point gradient formula.
We'll have to watch it.
So y equal 2 lots of 2 plus 6 all to the power of 3. Wow, this one's going to be one big y value. 4 plus 6, 10, 10. So the y value is 1,000. So there is a point on the curve that is 2, 1,000. Yeah, it does exist.
Groovy.
Good thing I'm not asking you to graph it.
Oh.
But theoretically, once you cover the
Well, you
stuff in the
could,
HC course, you can.
Oh, you could.
Alright, y take away y1
Yeah.
is m, x take away x1.
Look like it's
On
on
zero.
the line.
Yeah.
Or, do you guys want to make a hologram thing? You can make this, it's so cool. You get a CD case, and you cut out rhombuses, 4 of them, and you stick them together, and there's videos on YouTube, and you place it in the middle of your phone, and it makes a hologram through the thing, because it's 4 images on the side of the glass. Do you reckon we can convince
Oh,
people that it's
okay.
Oh, damn.
Hold on.
There you go. And the tangent crosses the y-axis at negative 200.
Photo